Everybody say hi, Maddie and Kelsey.
Hi, Maddie and Kelsey.
Hi, Maddie and Kelsey. Okay. All right, this is the last section, section 6.4, central limit theorem. Similar to what we did in section 6.1, 6.2. So we're kind of going back to that, but we're joining in 6.3 stuff where we talked about sampling things, okay? So this one is titled the central limit theorem. And let me kind of show you what's going on over here where we talk about earthquake depths, whatever depth means. I don't know, earthquake depths. Like how deep in the earth the fault line, whatever, okay? So this is the entire population. The one on the left is the entire population of all the earthquake depths, okay? And it's a pretty broad range, right? Like we have some depths that are like all the way out in here to like 30 kilometers. And then we've got some that are like only like 1 kilometer, right? Okay? And this is the entire population graph. And we can see that it is non-normal or not a normal distribution, right? What's a normal distribution? What does normal look like?
Bell curve.
Normal looks like a bell curve. That's uniform. Yes, I know exactly what you're talking about. Normal looks like this. Uniform distribution is where it's all the way across, like a straight line, okay? Normal distribution, that's what we're looking for, okay? But they are saying, yesterday we talked about sampling methods and like sampling stuff and how the mean is pretty well the same from a sample to a population, that type of thing, okay? They're saying if we take all of this information and we pull out a sample of like just 50 earthquakes rather than talking about all of them, right? All of the 1392 earthquakes, they say. There's 1392 in this graph. If we only pull out 50 of them, we are likely to get not these, right? And not these. We're likely to pull mostly numbers that are about average, right? Because there's more numbers that are average, right? There's more numbers that are here in the middle, so we're likely to pull those values rather than, we might get 1 or 2 that are up in this range, but most of the values that we pull from the population are going to be about average because there's more of them, right? So they're saying that if we pull out just 50 of them, what's going to happen is typically, even if your population is not a normal distribution, we're pulling out mostly average ones and we get something that is normally distributed with a sample. Does that make sense? Why that would be, right? Most of the numbers that we pull are going to be the numbers that are in the middle, and it is going to follow a bell-shaped curve looking thing, right? Okay? This chart that we look up on the negative and positive, right? You guys see this negative positive chart? This only works when you have like a bell-shaped curve or a normal distribution, right? That's why we have the bell-shaped curve at the top of each page. So we can't do that with this information, nor would we want to, because then we would have to look at more values, right? We want to look at samples, and samples are normally distributed. So that's kind of what the central limit theorem says. Up here at the top says that for all samples, as long as the sample size is greater than 30, right? We have to do at least 30 numbers in order to get a bell-shaped curve, a good bell-shaped curve. The sampling distribution can be approximately normally distributed. Even if the population is not, the sample will be like a bell-shaped curve. That's all they're saying there, okay? All right, let's go down here. And these formulas that are down here at the bottom, in order to do the central limit theorem stuff, we have to have a sample size that's greater than 30. That just has to be the thing. Otherwise, we don't have enough data values to have a bell-shaped curve, okay? We have to have a greater than 30 sample, okay? So, and then we have a little bit different formulas down here. The mean is just the mean. There's nothing different than the mean. They call the mean mu rather than x bar. That's what we're used to calling it. But that's just the same thing as the mean. So if you see that value, the mu instead, that just means find the average of these values, okay? Now the standard deviation that we calculate is a little bit different when we're doing the central limit theorem stuff than what we're doing normally, okay? The standard deviation, this guy is standard deviation. It's just, we call it normally S. They're calling it sigma. It's the circle with the hat on him, okay? And rather than just saying the straight standard deviation, we have to incorporate the sample in there. So we take this and divide by the square root of the sample, okay? And then this bottom one, the z-score, we before just did this part of z-score. Do you guys remember that formula? X minus x bar divided by the standard deviation. Yeah. But now our standard deviation is not just this. It is now this whole number, right? That's our whole standard deviation. So you're really just doing x minus x bar divided by the standard deviation, but now it's calculated that way. Okay, we'll do all examples of this. This is kind of a little bit confusing now. Okay. Yeah. So just a little bit different when we're doing central limit theorem. Okay. Yeah. Good. Let me show you how this is different than what we were doing before. Let's use an example. Are we ready to go to the back?
Yeah.
Yep.
Okay.
But
Yes.
the X bar minus the mu are the same thing.
So we'll talk about that.
Okay.
This is so X bar in this case is the sample mean, and X and mu is going to be your population mean. We'll talk about this. Okay. All right. So I'll lead with that here in a second.
Okay.
So sample mean, population mean. It's still kind of like your X and X bar. Okay. All right. Go to the back. Go to the back. Here's your example. Ready? I'm going to write down, there's a big paragraph here. I'm going to write down some information that we have off to the side over here so we don't have to reread. And what we would normally have happen is like we would talk about let's talk about weights of you guys. I'm not going to actually ask your weight, but let's talk about your weight because this example is talking about weight, okay? Let's talk about the weights of you guys. And we would talk about like z-scores in relationship to one person, okay? So you would like take your weight, convert it to a z-score, and then find what percent of people would be like heavier than you or less than you in the room, right? Like that. That's how we would do that, right? For weight. Now we're looking at a sample of not just one person. We're not just talking about just you. We're talking about like 27 people together and their average weight being more or less, right? Okay, so we're not just talking about one person. We're talking about a group of people. Like here we're doing 27 people. This is where the central limit theorem comes into play. We're not just talking about one individual value. Central limit theorem is taking a sample of 27 people. And that is why this formula has to incorporate this extra stuff right here, which is the square root of n, right? We have to incorporate that extra little value in there because we're not just doing one individual value, like your height or your weight. We're doing a group of values, okay? So here's how this works, okay? I'm going to go through, read this paragraph, and we're going to write some stuff down. And so we don't have to reread. The elevator in the car rental building at San Francisco International Airport has a placard stating the maximum capacity is 400 pounds. Okay? So the max weight equals 4,000 pounds. But then they also say at the same time that the maximum is 27 passengers or people, right? So this elevator says we can hold 4,000 pounds or 27 people. But if you divide that out, the average, which we call mu, is 4,000 divided by 27, which is saying on average 148 pounds per person, okay? Right? Now some of you guys are maybe thinking like 148, if that's the average, what happens if we have like an elevator that has 27 people in it? So we're still going off of that, but each one of them weighs more than 148 pounds. That's not good, right? We're going off of the maximum 27 people, right? But if each one of them weighs 148 pounds or more, we're going to overload this elevator, right? Okay, so that's bad. So that's kind of what we're talking about here in this conversation. We're not looking at just one person weighing more. We're looking at a group of people weighing more than the average, right? Okay, so this converts to the mean passenger weight of 148 pounds when the elevator is full. Here's our scenario. We will assume the worst case scenario, kind of like what I just described to you, in which the elevator is filled with 27 adult males. Why are we going to stuff adult males in there for a worst case scenario? They weigh more, right? Typically, adult males weigh more than adult females most of the time, right? Okay, they're just bigger. So we're going to stuff these adult males in there, like illustrating a worst case scenario, because most of them are going to weigh more than 148 pounds, right? I don't know if I know too many adult males that weigh less than 148 pounds, right? Right? Like none of you in here weigh, even Jackson, we pick on his height, right? He weighs more than 148 pounds, right? Right? Okay, so not a whole lot of the time does that happen, all right? Here's what they say. If we're talking about just one male, they have found that the average for just one male is 189 pounds. And if we have 27 that are average weight, each one of them is like 40 pounds over. So that's going to be quite a bit over the weight, right? Like if each one of them is 40 pounds over and we have 27 of them, that's like lots of pounds over, like 8,000 pounds over the 4,000 pound limit. Like that's I don't know, 800 pounds over the 4,000 pound limit. That's a lot. Standard deviation is 38 or 39. So our mu is the total, but X bar in this case is 189. Do you see that? Okay, so there's the difference between the two. Rather than using X and X bar, we do X bar and mu. So this is where the X is going to go. This is where the X bar used to go in our formula, right? Instead of X minus X bar divided by the standard deviation, we do X bar minus mu divided by the standard deviation. Do you see how that works? Yeah? Okay. All right, so in part A, just go back to what we would normally do, not taking into consideration we have 27 passengers. Find the probability that one adult male weighs greater than 148 pounds. Okay, just think in your head. If I'm talking about an adult male, and I'm talking about the probability of them weighing more than 148 pounds, what do you think? The probability of an adult male weighing more than 148 pounds. Pretty good chance. I'm going to guess like maybe 90%, right? Or 95%. Probably a pretty high probability, all right? So just doing what we normally did to find z-score, we have a value. This is just comparing what we normally did. We have a value that's 148. We convert next to a z-score. I wrote this at the top of you guys' papers the other day, some of you. And to convert to a z-score, and then we convert that to a percent, right? Or a probability. Percent and probability kind of mean the same thing, okay? So if we're converting 148 to a z-score using the normal formula that we were doing, we would take 148, subtract what? Oh, wait a second. Has a mean weight greater than 148. Okay. Actually, our value is not 148. Our value is 189. Yep. No. Wrong. I'm all sorts of confused here. 148 is our value. We're comparing it to 189. Woo! Okay, here we go. 148 minus 189 divided by standard deviation is 39. Yeah, we're okay. 148 minus 189 divided by 39. Does somebody have that number? It's like, I don't know, negative 1 point something. 1.05? Negative? Mm-hmm. Negative 1.05. Okay, so that's my z-score, negative 1.05. We're 1.05 standard deviations below the mean. All right, so if I'm looking at a bell curve, the average is 189. And I want to know the percent of people that are above 148, which means those people there, right? Okay. My z-score is negative 1.05. So from here, we look up on the chart and we say negative 1.05. 0.1469. Okay. So the percent is 0.1469 or 14.69%. Okay. What does that mean? 14.69 is less than us, right? 14.69% is here. I want to know what percent of people are greater than 189 pounds, or 148 pounds, I mean. 85.31. Greater equals 85 point, what'd you say, 31? 31. Were we close? In our guesstimation, we were like, oh, it's going to be probably a pretty high percentage, right? Chances of a man being over 148 pounds is probably pretty high. 84% of the time that happens, right? Okay. This is what we are used to doing in part A. This is what we're used to doing. But now we're going to look at the whole group of 27 people. What are the chances that all 27 people are going to exceed the 4,000 pound limit? Probably pretty high if we're dealing with all adult males, right? Okay. So find the probability that a sample of 27 randomly adult males has a mean weight greater than 148, okay? So I'm going to go back up to this information right here, and we're going to do the mean, standard deviation, z-score, okay? So mean is just mu. Standard deviation Instead of just using the standard deviation, we have to take the standard deviation and divide by the square root of n, okay? For z-score, we have to do, kind of similar to the same process we did, x minus mu now divided by the standard deviation over the square root of n, or this number, whatever that is, right? Okay, so just a little bit different formula, but the same kind of process. We still do value to z-score to percent or probability. Okay, value z-score percent. Okay, find the probability that a sample of 27 randomly selected adults has a mean weight that's greater than 148. Do you think that those 27 males are going to have a mean weight greater than 148? Do you think that that's going to be true? Yes. So I'm guessing that this percent is probably going to be pretty high. Okay? I usually ask myself that question, like, what will the answer probably be? I'm guessing that's going to be a pretty high percent. So if I end up getting a low percent, I'm probably going to look back on my work and make sure I did everything right. Okay? All right, so my value. My value that I'm working with is the 148. And 148 was the mu. I always get these confused. 148 and x bar. Which one's mu and which one's x bar? X bar is the sample. Ah, so these are switched around. Right? X bar is sample, mu is population. So which one is based upon the sample? What's the weight? No, we didn't do it wrong in A. We just named them, like named these wrong over here. So X bar is going to be 148. The mean, the other one is going to be 189. We had it right in part A after I switched it around. Yeah. Okay. So mu is 189. X bar is 148. Okay. Standard deviation is 39. Okay. We have to convert that to a z-score. So these are our values. We're converting that to a z-score, which we have a different formula for doing. Okay. Blah, 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 blah. Let's go. X bar is 148. Minus mu is 189 divided by 39 over the square root of, oh, what was n? 27. So just a little bit more work on the z-score part. We have to divide by the square root of 27, and that's going to give us something. I don't know. It's going to be like a crazy number, like 6 maybe or something. Negative, I don't know what it is. Okay, negative 5.46. That's my new z-score. So my z-score went from negative 1.05 to now negative 5.46. Okay, because we could possibly have a person, an adult male, weigh less than 148, but the chances that all 27 of them weigh less than 148, a z-score is going to be way more extreme, right? Okay, all right. So let's convert that to a percent. If I'm looking at this as a bell curve, I've got like my number down over here at negative 5.46 for my z-score. What's negative 5.46 on the negative side? All the way to the top, it says negative 3.5 and lower is like 0.0001 or something like that, right? Is that true?
Yeah.
Okay, but what does 0.001 stand for?
That's percent of.
Percent. 0.0001 is there, right? We want to know, find the probability that a sample of 27 weigh more than 148. So what percent of people weigh more than 148? 0.9999, right? Or 99.99%. So there is a 99.99% chance if you put 27 adult males in that thing, it's going to exceed the 4,000 pound limit. Does that make sense? So what should we do?
Not for 27.
Not put 27 on the thing. Just say 4,000 pounds. Or if we say 4,000 pounds, maybe instead do 20 people. Right? Does that make sense? Because if we say 20 people, then we might be under the limit, right? Okay? Because there's a 99.99% chance if we stuff that elevator full of 27 adult males, we're going to exceed the 4,000 pounds, right? What? Then the elevator will like stop and it won't move because it won't be able to like lift anybody up because it's too heavy. And then you get that like beep noise, and sometimes if the elevator doors are closed, then they're trapped in there and then they have to go get them out, and it's just a mess, right? So whatever, okay? Does this make sense? Same process as before, except we just have a different formula for calculating z-score, and we're looking at a group of people, their average, not just one person's height or weight, right? A group average. All right, let's go to the second one. This is the same process again. Just another example, we're talking about body temperature. Assume that the population of human body temperatures has a mean of 98.6, okay? So let's write down 98.6. That is a mean. Is that X bar or is that mu?
Mu.
Why?
Because it's not the population.
Because it's the population. Mu is population. So we're talking about population average is 98.6. They tell you that, right? 98.6 is supposed to be the average body temperature, as it's common believed. Also assume that the population standard deviation, which is this guy, is 0.62. That's the standard deviation they tell me, okay? If a sample size of 106, I'm collecting like temperatures on 106 people, I want to know the probability of getting a mean that is 98.2. Okay, this is going to be my X bar because we're talking about the sample now. I want to know the mean of getting, or the probability of getting a mean that's 98.2 or lower, okay? All right? If everybody on average has an average temperature of 98.6, what are the chances that the average of all of the 106 people are going to be lower than 98.2? I'll say that again. On average, everybody has a temperature of 98.6, and I am surveying 106 people. Those people all together having an average of 98.2, what are the chances of that happening?
Not too rare.
Probably pretty low. It is rare.
Oh, yeah.
Yeah. Right? These 106 people are going to have an average of 98.6, right? But if we say what's the chances that all of them average out to 98.2? Probably pretty low, right? Probably pretty low. Let's look, okay? So we're still doing values. To z-score, 2%. Okay, we have our values listed here. We have like an X bar and a mu and all that good stuff. Now we have to convert to z-score, okay? So let's subtract for z-score. What minus what? The formula is right here. What do we subtract?
98.2.
Right? 98.2 minus 98.6 divided by what? 0.62 over square root of 106. Okay, and we'll have to figure out what our z-score is. This one's like negative 6.64 or something like that. Check me. Because I'm looking at the chart. I'm cheating. Negative 6.64, just like the chart says, right? We're all the way down over there. Okay, so we have a bell curve. 98.6 they say is the average. That has a z-score of 0. We are over here at 98.2, and I don't want to know the percentage that they are lower than 98.2. Okay, negative 6.64 as a percent, if we look on the chart, is 0.0001, or moving the decimal 2 places is still 0.01%. So not even 1%, it's 0.01%. Okay, what does that mean? 0.01% chance of all 106 people having average temp What? Less than 98.2. Does that make sense? If the average is 98.6 and we're talking about all 106 of them having an average temp less than 98.2, that's not going to be accurate, right? It's like me saying, okay, on this next test, on average, the score for this next test is a 60, right? And you're optimistic and you're like, okay, I think all of us are going to average out to be over a 90. Probably unrealistic if it's the same test, right? Make sense?
Yeah.
Yeah, that's not going to be the case, right? I mean, you might be over a 90, right? But the average, if typically in past years, if it's a 60, your average class being over a 90 is probably going to be about a 60 because it's going to follow suit with what past data has been, right? Anyway, is this confusing? Maybe a little bit. If you read through it and listen to it, it's like that should make sense, right? Like the average male or the average person is 189 pounds. I want all of them to be under 148. That's not going to happen if the average is 189. Not going to happen. Okay, so there's how this works. Good? Questions before I stop the video? You guys have the homework assignment. It's just one-sided, right? There's only 3 problems, I think. They're not terribly difficult, but read through them and write stuff down. Anytime you see the word population mean, you're going to be using mu. Sample mean, you're going to be using X bar. Those are the 2 things that you're going to screw up if you screw up, right? Just keep in mind population mean, sample mean. Okay? All right, good. And then it's just value to z-score to percent. That's all you're doing. Good? Questions? All right, bye Maddie and Kelsey.